Let's now dig in to the first three basic angle properties in circle geometry. I'm going to prove them to you one by one, and afterwards, we're going to try to solve several questions using this theorem that you're going to learn. Okay, let's start with the first one. Here on the diagram, you can see that you have two angles inscribed out of the same 2 points, which are point A and point B. The first angle is angle AOB, where O is the center of the circle. The second angle is angle ACB, where C is at the circumference of the circle. The first theorem claims that the size of angle AOB is twice the size of angle ACB. Or, in sentence, I would write angle at the center is twice angle at the circumference. Let's try to prove it. In order to prove it, I need to draw a helping line from point C to O and extend it to point P. Now, let me draw your attention to angle ACO. Let's say angle ACO have a size of X. Now, can you find any other angle here that also have a size of X? Let me give you a hint. Look at this triangle AOC. Do you think triangle AOC is a spatial triangle? It is an isosceles triangle. Why? Because this line AO is the radius of the circle, and so does CO. So triangle AOC is actually an isosceles triangle because two of its sides are of equal length. So angle CAO will be equal to angle ACO because the two base angles of isosceles triangles are always equal. Now look at the third angle in that triangle. Can you calculate this angle, COA? It should be simple, right? You can calculate it simply by recalling that the total angle in a triangle is equal to 180 degrees. So COA is equal to 180 degrees minus 2x. And what about AOP here? AOP and COA adds up to a straight line. So, utilizing supplementary angles, you can calculate the size of angle AOP, which is 180 degrees minus the size of angle COA. You will get 2x there. Now, let's going to use exactly the same principle, but to the other triangle. If, let's say, the size of this angle in red is equals to y, can you do something similar to find the size of angle BOP? Yes, I'm sure you could do that. I'm not going to write all the details here all over again, but let me just show you that angle COB is again an isosceles triangle. So this angle will be equal to y, and angle BOP will be equal to y. Okay. Now, look at this angle AOB. The total size of angle AOB is equal to 2x plus 2y, while the size of angle ACB is equal to x plus y. So from here, clearly, you can say that angle AOB is twice angle ACB. That is the proof of the first theorem. You may not be required to do the proving all over again, but what you need to do with this theorem is to memorize it and use it in real questions later on. Let me now go to theorem number 2. On this diagram, I hope you can see that you also have two angles. We have angle AOB, which is angle at the center, and angle ACB, which is angle at the circumference. So this theorem is actually very similar to the first theorem, where you also have two angles. What you need to do here is to prove that angle ACB equals 90 degrees. In order to do that, let's recall the first theorem that we have just proven. The first theorem says that angle at the center is twice angle at the circumference, which means angle AOB is twice angle ACB. And we know for sure the size of angle AOB here because AOB is a straight line. So AOB equals 180 degrees. And that means angle ACB is half of it, which is 90 degrees. Or in another way, you can see here on the diagram, when I eliminate the lower half of the circle, you can see that triangle ACB is actually inscribed in a semicircle, just the upper side of the semicircle. So if I have to give this theorem a name, this is what it calls. ACB is equal to 90 degrees, and this angle is called angle in a semicircle, simply because angle ACB are inscribed within a half circle. And here comes the last theorem for the day. On this diagram, you can see two angles, but this time, both angles are angle at the circumference. I have angle ACB here and angle ADB. Let's try to prove that the size of angle ACB is equal to angle ADB. In order to do that, I would like to draw helping lines. Here are my helping lines. I have line AO and OB. Recalling theorem 1, we can see that angle AOB is actually angle at the center, while angle ACB is angle at the circumference. And the size of angle AOB is twice the size of angle ACB by theorem 1. Similarly, angle ADB is also angle at the circumference. So, by theorem 1, angle AOB is also twice the size of angle ADB, which means we can conclude that the size of angle ACB is equal to the size of angle ADB. So, theorem 3 is named as this. ACB equals ADB because they are angle in the same segment. Okay. Let me recall the meaning of segment earlier on. I told you that you can divide a circle into two sections by drawing a chord. Okay. So here I have a chord AB, and I have this blue area, which is called the minor segment, and the white area, which is called the major segment. So practically, this theorem 3 says that any angle at the circumference that you draw inside the major segment, which is the white section here, they will always have equal size. Look at another diagram here on the bottom right of the screen. I tried to inscribe an angle out of point A and point B. This angle will always be equal to any other angle at the circumference that are located in the white segment. I hope you can see this clearly.